Are you there?
Yes, I'm here.
Okay, so by definition, entropy is the degree of disorderliness of a system. Entropy is the degree of disorderliness of a system. You are taking it.
Yes.
It is designated by the symbol X, capital letter X, like you can see on the board. That's the symbol for entropy, and it's changed as this. That is triangle X. That's okay.
Yes.
Okay. Then triangle S is calculated as this, H over T. That is the formula for calculating entropy. That's one of the formulas. The other another formula that is mostly used for you. You can let the student also know this. That entropy change is enthalpy change divided by temperature. This T here stands for temperature, not time.
Okay. Enthalpy change over temperature.
Temperature in Kelvin, not Celsius. Is that it?
Yes.
Okay. So we said, what is enthalpy again? And we define this one before we finish enthalpy, before we enter entropy. And we say enthalpy is the total heat content of a system. Right?
Yes.
If we are saying enthalpy is the total, and entropy now is the degree of disorderliness. You can relate it to your class when teaching your students that even you agree with me that in the class, not all of them are ready to learn. In as much as the way I teach that is very interesting, I know myself that when I'm teaching, I know at least to some extent I carry students. But as I'm coming, my students are running away.
Also, they are everywhere.
Why some are inside the class just causing nuisance inside the class?
Exactly.
Those are like the entropy. So those ones are like the entropy of a system that causes disorderliness. So in a system, not everything inside that system wants it to work. So those particular particles are disorderliness in entropy. That's okay.
Yes.
You can explain it like that for your students. Let's go again to another one. This free energy gives. How do you spell it? Gives free energy, or some textbook will just say free energy. So this is the energy of a system that does useful work. That is to give free energy. It is the energy of a system that does useful work. Did you take it?
Yes.
Okay. The symbol for free energy is G, capital letter G. And the change is triangle G. Any question?
No.
Okay. Madam Esther.
Yes.
Have you seen this aspect in the scheme?
It's not there, but it's in. I've gone through it before.
Okay. So it's important to teach them. So even though it's not in the scheme, let us teach them. Okay, so let's go on. Now, why this? Mathematically, free energy is calculated. This is the formula now. Enthalpy change minus T entropy change. Is that okay?
Yes.
So this is the formula. You can write where triangle H is equals to enthalpy change, T equals to temperature in Kelvin, triangle S is entropy. That is what each of them stands for. Enthalpy, temperature in Kelvin, and entropy. Any question?
No.
Okay. Can I continue?
Carry on.
Okay. So write under it, note. Note.
Okay.
Number one, if triangle G, which is free energy change or this free energy change, is that okay?
Yes.
Is negative. Is negative. The reaction is spontaneous. Taking
Okay.
or visible, feasible. Any question?
No, no question.
No.
Number two, repeat this. The opposite of number one is number two. What would that be?
If delta
If
G is
delta G is positive, the reaction is not feasible.
Not feasible or non-spontaneous. Is that okay?
yes.
Yes.
Okay. Please, can see Madam Esther, like I always call her Madam Esther. The other one is Madam Techno. I don't know the name, please. If you help me with your name.
Sorry, praise God.
Sorry?
Praise God.
Okay, praise God. Thank you. So number three, under the notes. Number three. Are we ready?
Yes.
Yes.
If triangle G, that is this free energy, is 0. Is that okay?
Yes.
The reaction is in equilibrium. The reaction is in equilibrium. Someone is trying to say something. Are we good to go?
Yes.
Okay, so those are the three possible values you could get for free energy, and those are the interpretation. It's either it is positive or negative or 0. So let's look at some questions. Example 1. Can I start?
Yes.
Okay, if the change in free energy, okay, no, I wouldn't like to start with this one. Let's leave that one for example 2. Let's start with example 1 with this equation. 2 half N2 plus half O2. Half O2 will give me NO. That's okay?
Yes.
Another is to write enthalpy change equals to 89 kilojoules. 89 kilojoules per mole, comma. That's okay?
Yes.
Entropy change for the reaction above. Entropy change for the reaction above at 25 degrees Celsius is 11.8 joules. Entropy change for the reaction above at 25 degrees Celsius is 11.8 joules. That is J. Full stop. Calculate the change in free energy. Calculate the change in free energy. Are you ready?
Yes.
Calculate the change in free energy. That is A. Then the B part of that question. Can I continue?
Yes.
Okay. B part is state whether the reaction above, at 25 degrees Celsius is spontaneous, non-spontaneous, or at equilibrium. Are you ready?
Yes.
Give a reason for your answer. Give a reason for your answer. This is why theory question. Okay, so the first thing to write is your formula. Free energy is equals to triangle H minus triangle X, right? Madam, praise God. Can you hear me?
Yes, I can hear you.
So enthalpy change, what's our value for enthalpy change? I say where enthalpy change is what? We're given the enthalpy change as
89.
89 kilojoules per mole. What else again were we given? We're given
Delta S. We were given temperature and delta S.
so temperature is 25. Remember I said it must be in Kelvin. So you do plus 273, which will give me 298. Then the delta S, which is your change in enthalpy, as 11.8 joules. Right?
Yes.
Yes.
Okay, sorry. Let me just do something. Then by substitution, what do we have? So the next thing is to now substitute, say triangle G equals to 89 minus open bracket 298 times 11.8. Is that taken?
Yes.
Okay. If you have a calculator with you or your phone, you can use your phone, multiply what we have in the bracket. What do we have? We multiply.
3516.4.
Okay. That will give me 89 minus 3516.4. Then subtract, it will get minus what? Because of space. Minus. And it's going to be a minus. I'm waiting for you to give me the value.
Minus 3427.4.
Okay. 3427.4. Unit is kJ, kilojoules. Is that taken?
Yes.
No question, right?
No.
Okay. So we'll move on to the B part of the question. Are we ready?
Yes.
Yes.
Now, this is the trick there. In the B part of the question, a student can guess because it says state whether it is spontaneous, non-spontaneous, or at equilibrium. And they say give a reason for your answer. It is the reason that determines whether the child gets the mark. So when teaching them, this is how WAEC marks. So if a child is getting, for example, now, because it is negative, what did we say when it is negative?
That means it's spontaneous.
Good.
It's
You can say
spontaneous.
the reaction is spontaneous because free energy change is negative.
Negative.
So that is how it should be done.
So come again with the answer. The reaction is spontaneous because
The free energy change is negative because your value here is negative. That's why.
yes.
So the child cannot say it is spontaneous because the free energy change is positive. Even that the child said it is spontaneous, it is right, but the reason is wrong. So that will make the mark invalid for such a case. It is the reason that determines whether the child gets the mark correctly or not. Any question? Okay. Now I want to ask a question now because I've been asking any question. Nobody's asking a question. This is my thought. What do you mean by spontaneous reaction? Because we just said now that if the free energy change is negative or positive, it is either spontaneous or non-spontaneous. What is the word spontaneous even? What is a spontaneous reaction or a non-spontaneous reaction?
A spontaneous reaction
Yes.
is a reaction that is disorderly,
That what, please?
that is disordered or disorderly.
Yeah, okay. Okay. I don't know. But it's not correct.
Okay, let me try.
Okay.
Okay, try.
A spontaneous reaction is that reaction that starts with little or no heat content.
Okay. I will take the first part. And I will leave the other part. But the best or the correct answer is this. We learn every day. Let me start from there. Before now, I used to think that a spontaneous reaction is a reaction that is very fast. That is my thought.
Exactly.
Not until of recent that I got to realize that that is not even correct. Yeah. That's why
Yes.
I get to realize that I think I know everything in chemistry, but there are some things I still don't know because we learn. So a spontaneous reaction is a reaction that occurs without an external force.
Okay, yes.
That is, it occurs on its own.
Yes.
So obviously the opposite is not spontaneous. So Madam Esther, did you get it now?
Please come again with it.
A spontaneous reaction is a reaction that occurs without an external force. It occurs naturally. Why? A non-spontaneous reaction needs an external force for the reaction to occur. Is that it?
Yes.
Okay, so thank you. Let's move on to another example under this. So number 2 example. A chemical reaction with entropy change. A chemical reaction with entropy change of 20 kilojoules per mole. A chemical reaction with entropy change of 20 kJ per mole and free energy change of 55,000, that is 55,000 J. Are you there?
55,000.
Yes, 55,000, that is 55,000 J, that is not kilojoule, but J, occurred at -23 C. That is the temperature. Full stop. Calculate the enthalpy change. Calculate the enthalpy change. Is that taken?
Yes.
Okay, so let's get our formula right. Our formula is triangle G equals to triangle H minus T triangle X. So by the data given, G is equal to what? What's our free energy change? Was it given?
55,000.
55,000.
55,000 joules.
55,000. Enthalpy change, that is triangle G.
Is 20.
20 kilojoule per mole.
Are you sure?
Sorry,
No.
triangle G is
Sorry.
55,000.
Are you sure?
Yes, delta G is 55,000 joule.
Okay. What about delta H?
We are calculating.
No delta H, we are calculating it.
Okay. Delta
What
X,
was
55,000, 55,000. Then delta X,
It's
Delta
20
X is
kilojoule
20
per mole.
kJ.
20.
Yes.
T,
It's 23.
minus 23, not 20.
Minus 23.
Okay, okay. It's fine.
Plus 273. That gives us 250. Okay. So let's make H, delta H subject of formula. That would be what? Delta H by subject formula will give me delta G plus T delta X. If you still don't want to solve it like this, you can solve after you find H. You can use the formula directly to also get H. Whichever way you are okay with. Can we move on?
Yes.
So again, by substitution, I should now have delta H equals to 55,000. So that's my value for delta G minus T 250 times 20. This is 55. Okay, sorry, not minus, to plus rather. So 55,000 plus 20 times 250 should give me 5,000. Add it should give me 60,000 gain. So that is your enthalpy change. You can put plus in front of it because it's a positive value, or you leave it like that. Any question?
Okay, no.
Okay. I want to go to one interesting aspect now, which is types of enthalpy changes. Also not in the scheme, but it's important to do it. Types of enthalpy changes. Are we ready?
Yes.
Yes.
Okay, the first one is enthalpy, standard heat of formation, or you can simply say enthalpy of heat of formation, or standard heat of formation. As the first one, standard heat of formation. Are we ready?
Yes.
Okay. The symbol to use is this. Triangle H, theta. This is theta. Are you there? Then F. This F is for formation. If I write this, triangle theta, put X. S is for solution.
Solution.
So if I put this, theta H, and put N, neutralization. And if I write this, we'll get there one by one. C, that is combustion. So these are the 4 types of heat, or 4 types of enthalpy changes. But let's start with the first one, which is for formation. Are you there? Adames, can you hear me?
Yes, I can hear you.
Okay, so for this, you can write by definition, it is the enthalpy change. It is the enthalpy change when one mole of a compound is formed from its component elements. It is the enthalpy change when one mole of a compound is formed from its component elements under standard conditions of temperature and pressure.
From its components.
From its
Component under FPP.
From its component elements under standard temperature and pressure. When it is the enthalpy change, when one mole of a compound is formed from its component elements under standard temperature and pressure.
Okay.
Then number two.
Okay.
Number two, let's do combustion next. Standard heat of combustion. Are you there? In brackets, just remove this place of F and put C. That is the symbol. This is the heat released. This is the heat released when one mole of a compound This is the heat released when 1 mole of a compound is completely burnt.
Sorry.
This is the heat released. Underline that part, released. When 1 mole of a compound, 1 mole of a compound is completely burnt, B-U-R-N-T, is completely burnt in excess oxygen or air. When 1 mole of a compound is completely burnt in excess oxygen or air. Is that taken?
Yes.
This question came out last year. Why? And when we were marking, the emphasis was on excess air or oxygen. So if a student did not put that, it was a 2 marks for. If that is not there, the child gets 0 mark. So let them know. Okay, the device used for determining heat of combustion is bomb calorimeter. The device used for determining heat of combustion is bomb calorimeter. Bomb calorimeter. Do you get that? Madam Esther, do you get it? Then you can also still write, very important. Heat of the enthalpy change for heat of combustion is usually negative. The standard enthalpy change for heat of combustion is usually negative because the reaction is an exothermic reaction. That's okay. So we'll go to the next, which is enthalpy change, standard heat change or heat of neutralization. Oh God, I really wish I get to this calculation aspect before this time goes up. Like where I get there. Heat of neutralization. Madam S, are you there?
Yes, I'm here.
Okay. So heat of neutralization is the heat liberated. It is the heat liberated or liberated when 1 mole of hydrogen ion, from an acid reacts with 1 mole of hydroxyl ion from a base. When 1 mole of hydrogen ion from an acid reacts with 1 mole of hydrogen ion from the base to form 1 mole of water. To form 1 mole of water. Is that taken?
Yes.
So that is for neutralization. Because always you know this, neutralization is a reaction between an acid and a base to form salt and water. So the water is formed. If I have, for example, now HCl plus NaOH to give me H2O and NaCl, right?
Mm-hmm.
Did that take it? Then this HCl is same thing as HCl, we dissociate it, H plus, and this is minus. Why this Na plus, OH minus, we dissociate to give me H2O and NaCl. So this water now that is formed is as a result of this and this. And that's going to give me this water. Are you with me?
Yes.
So that is why we say it is the heat released when 1 mole of hydrogen ion from the acid, which is this one now, react with 1 mole of hydroxy ion, which is this, from the base, to give you 1 mole of water, which is this H2O you are seeing here. Did you get it?
Yes, I got it.
Are you tired?
No.
Okay. So heat of solution, the last, before we look at some calculations. But the time is up. Can I collect 20 minutes of your time? If this time goes also, we'll look at the calculation aspect.
Okay, no problem.
Okay. So we'll look at heat of solution next before we come back and just do the calculation aspect. Heat of solution. This is the heat liberated or absorbed. This is the heat liberated or absorbed. Absorbed, not absorbed is AB, not AD. Absorbed when 1 mole of a substance dissolves in a known amount of solvent. This is the heat liberated or absorbed when 1 mole of a substance dissolves in a known amount of solvent. That's okay.
Yes.
Okay. So we can now write work examples, like we are looking at examples now. These examples could be from any of these 8 of enthalpy changes. Could be for solution, for interaction, depending on them. You just look at, I have about 7 or 8 or 9, depending on how many we can do before the time goes up. And I told you before, we'll shut down now and come back to just finish up in the next 20 minutes. But let's continue till the time goes up, right?
Okay.
Okay, so example 1. Let's start from simple to complex. If 32.0 gram of anhydrous CuSO4, if 32 gram of anhydrous CuSO4 dissolved in 1 dm cube of water, dissolved in 1 dm cube of water. Are you with me?
Yes.
Generated 13.0 kg of heat, HEAT. Generated 13.0 kg of heat. Full stop. What is the heat of solution? What is the heat of the solution?
Okay.
Open a bracket and write Cu equals 64, S32, O16. Okay, I can finish this question with less than 4 minutes since I already have 4 minutes. Did you get the question?
Yes, I did.
Okay, so the question was heat of solution. What's the definition of heat of solution?
Is the heat absorbed or liberated
Yes.
when 1 mole of a substance dissolve in a known amount of solvent?
Okay, I love that. When 1 mole, emphasis on 1 mole of a substance. So remember,
Yes.
number of moles. What is the formula for number of moles? Mass over molar mass.
Mass.
So I'm going to do this now. Say number of moles of the compound there is CuSO4. They said anhydrous, that means it does not contain water of crystallization. That's why it's just CuSO4. Then
Okay.
we're given the mass of CuSO4 to be what?
To be 13.0.
32.
Is it 32 or
Yes.
13?
If 32.032.
Okay.
If you wrote 13, please correct it. It is if 32 gram. Okay. Then molar mass of CuSO4. Cu is 64, right?
Yes.
That will be 64 plus 32 bracket 16 times plus 16 times 4. You can add that. If you do that addition and everything, as you get 160. Then 32 divided by 160 should give me. Are you with the calculator there? Or you can use your phone now. Okay. That should be 0.2 anyway. 0.2 moles. Any question?
No, no question.
Okay. Now we move on. That means 0.2 moles will give us a certain amount of heat, which was in the question, to be what?
$13.0.
Okay, 13.0. They now ask us to calculate the heat of solution. Remember, heat of solution is always 1 mole. So if 0.2 is this, and I say 1 mole equals question mark. And if you cross multiply and then divide both sides, you should be having, that is 0.2 over 13. You do that. 0.2 over 13 or 13. Sorry, that's 13. That's 13, not 0.2. Because 13 over 0.2. Are you with me?
Yes. I got confused there before.
Okay, where exactly? Let me know.
No, when you said 0.2 over 13,
Okay,
I got.
okay. So that will give you 65.0 kilojoules per mole. That is the heat of solution.
Okay.
That's your answer. So let's allow the time go off. We'll come back and see how many examples more we can do before we call it a wrap. Can you hear me?
Yes, I can hear you.
Okay, so just allowing the time to just run up because it's